What does that mean? That's exactly what I said. What does it mean though?
Well, it kind of lets you know if the average is skewed.
Okay. So here is an example of what we did when we talked about the standard deviation, right? Let's talk about it real quick. And here's what standard deviation says. Standard meaning in statistics, the word standard means normal. All right. So when we say anything in statistics, and we talk about standard, we're talking about something that is normal. Well, normal is a fancy word for any kind of average. It really means just average. Now, the normal curve has its own type of average, but when we talk about this in statistics, we talk about normal and the word average. They're the same things. So when I ask you to find a standard deviation, I'm actually asking you to find the standard meaning average, the average deviation from the mean. And so when we talk about a deviation from the mean, we need to realize that in this particular example, for instance, I have these 5 scores, right? And I want them to work out to where I got a mean of 70. So my mean for this, remember we call the mean X bar of a sample. This is called X bar, it's the mean, right? So I want to know on average, how far are these 5 scores deviating from the mean? Deviating from the mean. When you deviate, that means you go away from it. So we need to find the distance away from the mean. Well, here's what we did. We took every one of these values and did what? We subtracted them from 70, right? What happened when we did that? Some of these values were negative and some were positive, right? Why is a score of 57 negative 13? Can anybody tell me that?
It's less than the average.
It's less than the average. Why is a score of 82 positive 12?
It's higher.
It's higher. So we understand that there's going to be some that are lower than the average, some that are higher than the average. If I want to find the average standard, the average deviation from the mean, well, how do I find the average deviation? Here are all your deviations. What can I do? Add them all up and divide by the total, right? The problem with that is when we tried to add all these up, what number did we get? We got 0, right? That was a problem. All right, so how do we fix it? Well, we said that the reason that we're getting 0 is because some of these are negative and some are positive. So how do you fix that? You square it. Squaring makes them all positive, and it also makes any value that's very far away from the mean, such as negative 13, a very big positive number, right? A very big positive number. Everybody got that? Now, once we did this, we added all these up. Now we can add up all the squared deviations. These are the squared deviations because you squared these numbers and you got all these deviations squared now. Take that and divide it by the total. That value that we got right here was called a variance. It's called the variance, and it's the squared deviations from the mean. It's the average squared deviation from the mean. The problem with a squared deviation is that it makes no sense in terms of what we're talking about. In particular, this is squared test scores. There's no such thing as a squared test score, right? So how do we fix that? Well, if I want to undo a square, I take its square root. And when you take the square root, you get what's called the standard deviation. And this is the average deviation from the mean. So the average deviation from the mean is 8.69 points in this particular case. Now, the problem with this, though, is that it's assuming that we're talking about a population. We know that these 5 scores are not the population. Remember, a population is the big picture. This is a sample of those scores. And because it's a sample, these values that they're giving me are too exact. They're too exact. They're biased, we call biased estimates. So both these values, the variance, which is known as, by the way, the variance, which was the square deviations from the mean, the average square deviation from the mean, it's called sigma squared x. The standard deviation is called sigma x. They're biased estimates. We want to use their unbiased estimates, the sample values. The sample variance is called s squared of x. The sample standard deviation is called s of x. The only thing that's different about these two values, we find them the exact way. We find a mean first, we find deviations, we square deviations, but instead of dividing by the total, we have 5 values, but we divide by total to get the actual average. Instead of doing that, we always divide by 1 less. If you divide by 1 less, it makes this number out here a little bit bigger than this number over here. This is called the sample variance. It is the average squared deviation away from the mean. The problem with the average squared deviation, again, is that the average squared deviation does not make sense. And because it doesn't make sense, we need to fix that, right? We need to fix that. So to fix that, again, we take the square root. By taking the square root, we get the standard deviation known as S of X. And notice that this value right here, 9.72, is a little bit bigger than this value, 8.69. But what we're saying is that the average deviation from 70 is 9.72. That is what we talked about when we talked about standard deviation. And the reason I'm talking about that is because tonight I'm going to introduce you to more. I'm going to introduce you how to use standard deviation. In particular, when we deal with two things. All right, in particular when we deal with two things. So we're going to talk about an application of standard deviations and then a couple of rules that involve standard deviation. So getting out of this. And I want to look at this now. So here's what we have. It says, a sample of 20 students, end of the year was taken from 3 different teachers. Their end of the year scores were taken from 3 different teachers. The results are displayed to the right of the 3 teachers. Which teachers tend to be more consistent with their scores? So if you notice this, look at these right here. You have 3 different teachers, and I want to know who's more consistent. When I ask you about more consistent, what do you think more consistent mean? Can anybody tell me what do you think more consistent means? Anybody?
Repeating often.
Okay, so they can repeat often. Good. So it means you're talking about looking at a mode possibly, right? What else? Anybody got any other ideas?
Maybe the standard deviation is smaller.
You want a smaller standard deviation. That's what I want to hear. Good. A small standard deviation means that the values all are close to what? They're all close to what?
The mean.
The mean. Good. And I want everybody to understand that. I don't know what the mean is for either one of these data sets right now. Don't know what it is. Right? But I do know for this particular problem, I do know that I want to find a mean, and I want to know how far each one varies away from that mean. So I want to find the standard deviation for each one of these particular data sets. Now, I'm not going to find the standard deviation by hand anymore, because I want you to find it by hand because I want you to understand what it is. But I want everybody to understand that what you're measuring is the average spread or the average distance away from the mean. So we're going to go find the standard deviation using Excel for all of these. Everybody got that? And notice that it's a sample of how many students again? It's a sample, right?
20.
So it's a sample of 20 students. Everybody understand that? And I want everybody to understand why does that matter? Because it's a sample, because these are samples. Because it's samples, you need to use S of X. You need to use S of X. If this were the population, you would be using sigma X. That matters. And when you do it in Excel, it's going to matter as well, all right? And then we're going to talk about this other thing called the coefficient of variation. And the coefficient of variation is actually what I want to get to, but I'll get to that in a second. So it says my internet connection is unstable. Y'all can all still
you're
see me,
pretty
right?
choppy.
I'm pretty choppy right now.
It sounds very computers too.
I feel very
I
confused.
can see your screen, but I can see your video.
You can see my video. What do you see right now?
The numbers you got on your screen.
All right, that's what I have on my screen. Am I that bad off right now, you guys? Y'all can't. Can y'all hear me though?
Nah, it's okay.
Right
It's
now,
okay.
no, you
You're
were
just
earlier.
chopping off a little bit. You're just lagging
Okay.
a little bit.
Cool. Let me see. Hold on. I'm trying to let people in still too. All right, so I'm going to talk about this thing called the coefficient of variation first, all right? The coefficient of variation, and we're going to find the sample. We're going to find the standard deviation. I'm going to compare those two, but the coefficient of variation is a measure of relative variability. So it's called the coefficient of variation. You may see it written as CV. And it's a measure of relative variability. What do I mean by relative variability? I want to know how much variability do you have in your data relative to the mean. And I'm going to use the standard deviation to do that. All right. So I want to know how much variability is in the data. So your variability here is it's going to, the variability is measured using the standard deviation. I'm not gonna write all that. Standard deviation S of X. The variability is measured using the standard deviation S of X relative to X bar. And it's always expressed as a percentage. It's always expressed as a percentage. And the value itself is equal to this right here. The coefficient of variation, CV, is equal to the standard deviation, S of X, over the mean, X bar, times 100. And so what we have to find, and what we're going to do is this: we're going to use two measures to determine variability. All right, we're going to use two measures to determine variability in this particular case, or to determine how consistent things are. I'm going to use the standard deviation as one measure. I'm going to also use the coefficient of variation. And you could think of coefficient of variation if you deal with, like, for instance, with stocks. A smaller coefficient of variation means your stock is less variable, or in terms of less variability, that means that you have less risk. Does that make sense? If a stock is less variable, you know what it tends to do. There's going to be less risk there. The higher the coefficient of variation, the more risk that is involved there. So you can think of this coefficient of variation that I'm telling you about right now as a value that measures risk. And in turn, that means, so the other part of that is, because it measures risk, it also measures consistency as well. The smaller the value, the more consistent. The larger the value, the less consistent. So what we're going to do is we're going to open up that, let me bring up my screen. Share screen. Share that. All right, so we're gonna look at this coefficient of variation data, and we're gonna fill out all of these, what we call our summary statistics, by the way, for each teacher. So we're gonna find the mean, the standard deviation, the minimum, Q1, median, Q3, and the max. Y'all remember what these are called right here? Does anybody remember what those are called? We talked about those. You remember what that's called?
The quartiles?
That's close. You're there. Q1, median, Q3 are the quartiles. It's actually called the 5-number summary. That's called the 5-number summary, right? We're gonna talk about the shape. How do we find shape again? Remember how we find the shape? There's 3 shapes. How do we find them? Anybody? What are the 3 shapes? Anybody can remind me?
Using the
Left
graphs.
skew,
or
right skew,
right
and
Good.
symmetric.
Left skew, right skew, and symmetric, right?
Symmetric.
And we're
Yeah,
gonna look at the mean. So we're gonna look
and
at
the
that mean
mode.
and that median, right? We're gonna look at
Yeah.
that mean and that median, and we're gonna talk about, we're gonna compare them. We want to see, compare the mean compared to the median. Is it less than the median? Is it greater than the median? Or is it equal to the median? We'll find the range, and we'll talk about the IQR as well. All right. So let's go find all these values. Let's start off with teacher A. To find the mean, we're just gonna use formulas here. So equals, I'm gonna do the average, because that's what mean is. Teacher A here. There. Teacher A's average is 74. If you drag these over, they should copy to the other ones as well. So who has the higher average right now?
Teacher B.
Teacher B, right? Now, let's talk about how spread out each value is from the mean. We're going to talk about the average deviation from the mean now, so standard deviation. So if you start typing in the word standard deviation, notice this: you have standard deviation P and standard deviation S. P is for a population, S is for a sample. What do we have here? A population or a sample?
Sample.
We have a sample. So we'll do standard deviation S. We'll drag the numbers down again like this. Close that. We get this right here for teacher A. Drag across. There you go. Right now, who looks to be more consistent? A or B? I mean, A, B, or C?
A.
Hey, teacher A looks to be more consistent, right? Which means that their values are closer to the mean, right? Even though teacher B has a higher mean, the values of A are closer to the mean. So we can find these other values. Here, I think minimum is a function. Yeah, you have minimum as a function here. Drag down again over these values. That's the minimum. Drag across these values. There go those.
What was that formula for minimum again?
Just minimum, M-I-N.
Okay,
You start typing, it'll come
gotcha.
up.
Okay.
Q1, there is a quartile function. It's called exclusive and inclusive, EXC and INC. I'll be honest and tell you, I don't remember which one I'm supposed to be using. 1, 2, 3. There are how many? There's 20, right? So quartile 1 should be 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 74 and a half. All right, here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. So it should be 71 and a half. Let's figure out which one it's supposed to be. Let's see if it's that one first. Q1, so you type in the word quartile, you have quartile EXE, and the function works like this. It asks you for the actual value. So here's my values. I want to find the quartiles out of here. I want you can either find the first quartile, which is the 25th percentile. You see that? Oh man, I got somebody sitting in the waiting room on my phone. You can either find the first quartile, the median, or the third quartile. Y'all see that? You have to give it a number, so I'm going to give it 1. I want to find the first quartile here. Close that. That's not the right one. It's 71.25. So let me try it again. I use EXE, right? On that one?
Yes.
Yeah, let's do I and C. Quartile. Again, drag down. This time I'm doing I and C. I think that's the right one. I want the first quartile. Yeah. That's not right either. Equals. Let's use this compatibility function and see what happens. Use INC. Use the INC function. It doesn't matter how you do it. Excel calculates its quartiles a little bit differently. And I don't want y'all to get hung up on that. I should get, my actual quartile 1 is between 71 and 72. So it should be 71 and a half. We were calculating it by hand. But again, I don't want you to get hung up on that. So use the INC function for that when you calculate your quartiles. And the only time you do is Q1 and Q3. They should be really close. They should be really close. You may be off a little bit, but that won't affect a whole lot of what we're trying to do. All right. So I don't want you to worry about that. Use the INC function. The next one, the median. I'm going to use the median function. I need to drag across, by the way, I'm sorry. Drag those across. Drag these medians across. There you go. Q3, again, use the quartile function. INC. This time though, when you do it, you're gonna drag across your numbers that you want. This time though, you're trying to find the third quartile. You're trying to find the third quartile. So you type a 3 in on the back of that. Everybody got that? Type the 3 in the back and close that. There's your third quartile.
So if you did the second one under the quartile, is that going to give you like the second and third together?
That'll give you the median. You mean like the 2? Is that what you mean? Like when I type it in, for instance, you're saying when I do use that function, let me highlight this. If I did number 2, where it says median value, is that what you mean? What do you mean?
Yes.
I'm sorry. Yeah, if you do 2,
Yes.
it should give you, yeah, you see I give you the median right above it.
Gotcha.
That's what it's doing. It's giving you that. I don't want the mean. I want Q3. So yeah, all it's doing is it's giving you whatever quartile you're asking for. We only want the first and the third. There you go. Max value. There's a max function. You can also use the quartile functions if you want to, by the way. Because I just saw that you could type a 5 and it gets to that. Yeah, it keeps telling me my internet is unstable. So if it is unstable and you don't hear something, please ask me to repeat it. You know, there goes your max. Now, coefficient of variation. A couple ways we can do it. We have a formula. Excel might actually have a formula. Let me see if Excel has a formula. It does
I
not.
couldn't find it.
Yeah, I don't think it has one. So we have to calculate it by hand. And it's easy to calculate though. It's just the standard deviation divided by the mean times 100. So we're gonna take the standard deviation, which is this value right here, divide that by the mean, which is this value here. And we're gonna multiply that by 100 to make it a percent.
Okay, so I have a question.
I'm listening.
So you see the standard deviation and it's like 10.4222. You don't
Yes,
change
ma'am.
those anything, you just do it as is, correct?
Right. Especially like on Blackboard. Blackboard's going to ask you to, I mean, not Blackboard, my math lab is going to ask you to give it to a certain decimal. So like if I tell you to give me 3 decimals, you would call us 10.42, you would round that to 0.423. You see what I'm saying? So on my math lab on the homework, they tell you to give it to a certain amount. So make sure that when you calculate, you're calculating to that correct amount. Because if you don't, it'll mark it wrong. I go your coefficient of variation. These are percentages, by the way. You should be able to drag. I think you should be able to drag. Yeah, you should be able to drag, and there you go. Your coefficient of variation should line up for the most part with your standard deviations. And what I mean by that is this. Notice here, the smaller standard deviation for teacher A also had the smaller coefficient of variation. The smallest, the second smallest, teacher V, had the second smallest here. The largest had the largest here. They should pretty much line up for the most part. This right here, this value right here, is going to tell me who is more consistent. This is what I mean by consistency. All right, the smaller value means that they are more consistent. That's what I'm asking for. I want to know who has that smaller value. So in this particular case, if I ask you what teacher is more consistent with their grades, you would tell me teacher A. Right? And that's why are you telling me teacher A? You can tell me I want 2 reasons why. Here are the 2 reasons. Teacher A has the smaller standard deviation. Teacher A also has the smallest coefficient of variation. All right. So I want both those reasons. Don't just tell me because of the standard deviation. And I'm telling you that because your first project, and I'm going to give you an Excel, is going to ask you about consistency. And the first thing you're going to tell me is that it's this particular company because I shouldn't tell you that, but you're going to tell me this particular thing, this particular reason because of the standard deviation. That's all you're going to say. And it's more than just the standard deviation. When you measure consistency, or when you measure which ones are less risk averse, those type of things. You're looking at the standard deviation, and you're also looking at the coefficient of variation. Here we can write our shapes in now. Comparing our shapes, compare the mean to the median, 74, 74 and a half, those are pretty much the same. So 74 here, 74 and a half here at the median. Let me highlight the median row so we see that. Let's go with there. Let's go with a mean. Let's highlight that in.
I have a small question with the very first part.
I'm listening.
That on the left side, how we have numbers with teacher A, B, and C.
Yes, sir.
On the right side, did you use any formula, or it just calculates it when you stretch it from left to right?
You
for
stretch
each?
it. I stretched it. I only did A for each one of these. I only did A, and then as I did it, it moved it over.
So how
So
does it know what you
it knows
want?
because it knows how to calculate. Well, it sees. So like what it did was here. That's a good question. I don't know. I don't know how Excel knows, but Excel knows that Excel
Teacher
knows
A,
that when I do teacher A right here,
Mhm.
if I drag it across, it's going to do teacher B here and the teacher C here. I don't
Does
know how Excel know that, but it knows.
Is it because you wrote teacher A, teacher B, and teacher C on the side? It just
Nah,
or-
nah, I don't think Excel can read it like that. I just know that I know when I do here, if I drag across, it's just calculating. What it's really doing is just moving. If I did, like in this particular one, I did A to the A21, because I dragged across, it did B2 to B21.
Okay.
And because
Okay.
I dragged across from there, it did C2 to C21. You see what I'm saying?
Yes.
It's just
So,
copying the same thing. It's just moving the actual letters from the next thing.
got you. So it's doing
All right.
3 sides on this way from the 3 sides on that side.
Right. That's what it's doing here.
Okay.
So now the shapes in. When we look at our shapes, compare the red to the gold, 74, 74 and a half, about the same. We're going to call that symmetric. 76.75. So the mean here is bigger than the median. The mean is bigger than the median. When the mean is bigger than the median, what's that shape? Can anybody tell me?
Right skewed?
Right skew.
Right skewed. That is right skewed. When the mean is greater than the median, remember your mean is always in the your mean always lies in the direction of the skew. So if it's on the right, if your mean is greater, it's on the right, it's going to be right skewed. 74.7, 76, we're going to call that. The mean here is less than the median. That's going to be
Left skewed.
left skewed. There you go. If I want to find the range is also another measure of variability. It's not a very good measure of variability, but it is a measure of variability. If I want to find the range, I take the max value, subtract it from the min value. That's one way to do it. There is a formula for range, I think. Is there? I guess not. We don't need it. There goes your range. Again, for the most part, they should line up with the standard deviation and the coefficient of variation as well. So the smaller range should belong to the more consistent values. It's typical of what consistency is. The last thing is the IQR. Can anybody tell me what the IQR is?
The interquartile range,
Interquartile range. What does that mean? Interquartile range.
the second and third one.
That's between the second and third. So that's between the first and third, right? Between the first and third quartiles, the middle 50% of the data. The middle 50% of the data. So to find it, we take the range from Q3 minus Q1. Q3 minus Q1. We get this value, 6.25, drag across. Again, this is another value that should line up with consistency. The smaller value should belong to the one that has a smaller range, a smaller coefficient of variation, and also a smaller standard deviation. It means that the values are very close together. All right. So if I'm asking you to measure consistency, I'm asking you to look at two things, standard deviation and the coefficient of variation. Those two things are very important when I talk about consistency. Anybody got any questions on this particular part?
No, sir.
All right, let's go to the next part then. So now that we know how to find a standard deviation, we're gonna actually do something with it. And what we do with it is going to be based off of the shape of the distribution. We're gonna start off with our shape of our distribution. And in particular, I am interested in something that is going to be what we call normal, right? Normal. So we have this rule called the empirical rule, and it only works. The distribution of the data must be approximately normal. The distribution has to be approximately normal for this to work. Or when I say normal, I really mean that it has to be this bell shape, right? It's bell shape. So the distribution is normal or bell shape. I can use what's called the empirical rule to estimate percentages. What do I mean by that? Estimate percentages. Well, here's an example. Let's drop down all the way to the bottom down here real quick. The distribution of IQ scores is approximately normal. Most people have an IQ, by the way, with a mean of 100 and a standard deviation of, that should be 15. I don't know why I didn't put that. This should be a standard deviation. Let me write that out. Standard deviation equal to 15. We have a standard deviation equal to 15. If 1,000 people are in a population, how many people would you expect to be labeled as genius or having an IQ greater than 130? So here's how this works. Every normal curve by definition is symmetric. It's symmetric. And what do I mean by symmetric? Can somebody tell me what I mean by symmetric?
The mean and the median are equal.
Good, the mean and the median are equal, right? And in a normal curve, the mean always lies at the middle of the curve. So if we take a normal curve, we get this bell-shaped curve. Get this bell-shaped curve. And the mean is always, the mean, we're gonna talk about the population mean, we call it mu. Do y'all remember us talking about the population mean as being mu? Or is that something I made up?
No, you talked about it.
Okay, good. So if you don't know what mu is equal to the population mean. Now, on this particular curve, it drops at certain places. It's symmetric. So it's going to drop at 3 different places on both sides of the curve. Drops here, and then drops one more time out here. Same thing over here. Drops here, and then one more time out here. So to the right, of where it's dropping at, like this, there are, where it's dropping at is what we call our standard deviations. So this is 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. To the left is also standard deviations. To the left is also standard deviations. And again, that's 3 standard deviations away to the left, where this is -1 standard deviation away, -2 standard deviations away, -3 standard deviations away. This is important to begin with, because what this tells me is that every normal curve, in order to get this particular shape, by the way, that's why this works. In order to get this particular bell shape, every normal curve has exactly, or has approximately, we'll say approximately 6 standard deviations underneath it. It has approximately 6 standard deviations underneath. So this is a total of 6 sigma underneath there. That's 6 standard deviations underneath the curve. Every normal curve is 6 standard deviations underneath the curve. All right, there's 3 to the right and 3 to the left. They're symmetric. So what this really means then is, because I know this, I'm able to accurately find how much data sits within each standard deviation. And I can do that using the empirical rule. And what the empirical rule says is, within 1 standard deviation of the mean, and within means that it can be either to the left or to the right. Within 1 standard deviation means it can be to the left or to the right. So within 1 standard deviation, which is right here, within 1 standard deviation is 68% of the data. In order to get this shape, in order to get this bell shape, 68% of the data has to lie within 1 standard deviation. That means I'm looking at people's IQs, and I have 1,000 people. What is 68% of 1,000? Can anybody tell me that? Anybody tell me what 68% of 1,000?
680.
680 people, basically. So look, what that means is this. If I look at this curve right here, 680 people have to lie inside of here. That's 680 people that sit inside of here. And we'll do something with this in a second. Actually, we'll do it right now. This says that the distribution of IQ scores is normal with a mean of 100. Where does that mean sit at? Can anybody tell me that? Where does the mean sit at? Because it's a normal curve, where does the mean sit?
In the middle.
In the middle. So I know the mean is at 100. And now here's what it tells me, the standard deviation. What is the standard deviation again? That is the average deviation from the mean. Well, the average deviation from the mean here is going to be 15. So how do I use that? Well, if it's 15, I know within 1 standard deviation, then to the left of 100 would be what?
85.
85. How did I get that? I just subtracted off 15, right? To the right of 100 would be what?
115.
115. So what does this mean? In a population of 1,000 people, we'd expect 680 people to have IQs between what?
85 and 115.
85 and then 115. That's what this is saying. In a population of 1,000 people, we'd expect 680 of those people to have IQs between 85 and 115. It gets better though, because what we can do now is we can keep extending this out. And the next thing we can say is that, well, within 2 standard deviations of the mean, within 2 standard deviations of the mean is 95% of all people or all the data. 95% of all data sits within 2 standard deviations of the mean. So 95% of all the data sits within 2 standard deviations of the mean. That means this, 95% is within 2 standard deviations, only 5% of the data does not sit within that. And furthermore, we can spread it out, we can separate it into how much sits within each one of these standard deviations out here. Remember, here's your mean mu, here is mu. This is 1 sigma, this is -1 sigma. So within there is, look right here, if it's 68% sitting inside of here, right? That means that within -1 sigma, from the mean to -1 sigma is 34%. From the mean to +1 sigma is 34%. Can anybody tell me why?
Because you divided 68% in half,
Why did I divide it in half?
because it's a normal bell, and that would be
And
the
the
middle.
bell is what though? We know that the shape is what?
Symmetrical.
What's this? It's good, it's symmetric. Because it's symmetric, we can divide it in half. We can cut everything in half here. It has to be equal on both sides. That's definition of symmetry. So the same thing applies this then. Now, within 2 standard deviations, within -2 to +2 is 95% of the data. Because there's 95% of the data, we can subtract 95 minus 68 and get 27%. And I'm doing that because I want to see how much is this green part, by the way. So the 2 greens together make up 27%. So I need to divide that by 2. That's how I get at 13.5%. So there's 13.5% of people that sit between those, that sit within each one of those different standard deviations. So again, if we come down here and look at this, well, within 2 standard deviations, so if I go to the left again of 85, what number am I at? That's 70, right? If I go to the right of 115, I'm at 130.
30.
And if I look at that like this, then within 2 standard deviations and 95% of all people, how many people have IQs between 70 and 130?
950.
950 people have IQs there. Would you say that most people have an IQ between 70 and 130? Yes or no?
Yeah.
Yes.
Probably so. Most people have an IQ between 70 and 130. Majority of people have IQs between 70 and 130, by the way. Keep going. We go out one more time right here. Within 3 standard deviations of the data. So within 3 standard deviations of the data. So at -3 sigma and +3 sigma is 99.7% of all the values. 99.7% of all the values sit out there. Hey, question, is that 100% of the values, yes or no?
No.
No, is it very close to it though?
Yes.
Yes. How much data does not sit within 3 standard deviations then? How much data doesn't sit within 3 standard deviations? 0.3%.
3%.
0.3%. What if they did at 0.3 though? It's 0.3 on both sides, right? You have to divide that in half. So on this side is 0.15% is out here. on the other side is also 0.15%. This is the entire normal curve, and this uses the empirical rule to establish everything about it. And now what we can do is we can say this, coming back down here, one more time, within 3 standard deviations in.
So it would be 25 people with an IQ greater
Good.
than 130.
Good, you're too fast. That's the answer. So let's go here. So 70, subtract 15, that's 55. 130, add 15, that's 145, right? How many people have IQs between 55 and 145? If you look at 1,000 people, 997 people. Would you say pretty much everybody you know, majority of the world has IQs that are between 55 and 145?
Yes.
Probably. Very few people probably know anybody that has an IQ lower than 55. Very few people probably know anybody that has an IQ greater than 145. Most people, pretty much everybody knows has an IQ there. This basically says how many people don't have IQ sitting inside of there? 3 people. 3 people. And generally speaking, what happens, we start to label those people. This is how we get our labels based off the normal curve, by the way. So the question was asked though, here, having an IQ, being labeled as a genius, having an IQ greater than 130. Well, if you go to your chart here, you can see that having an IQ greater than 130 is anybody out here, right? Anybody out here. All we have to do now is correspond this right here to this up here. You notice we have the 2.35. We also have the 0.15. So you have your 2.35 sitting here and the 0.15 here. And as somebody said earlier, I don't know who it was, I think it was Autumn. But all you have to do now is add these 2 values up. All of these people have IQs that are what?
Greater than
Greater than 130. So these are the genius people. So what percentage of people have IQs greater than 130?
3.5.
2.5% have an IQ greater than 130. But the question was, how many people? How many people would you expect to be labeled as genius then? So 2.5% have IQ greater than 130. How many people are labeled as genius? Well, that's 2.5%, which is, as a decimal, is 0.025, by the way, times 1,000 people is equal to 25 people are labeled as genius. And that's how we use the empirical rule based off a normal distribution. And you can only use the empirical rule if the distribution is known to be normal. It's known to be normal. So let's look at the other example, and we'll talk about that one. It says the distribution of heights for American women follows a bell-shaped and symmetric curve with an average of 64.2 inches and with a standard deviation of 2.9 inches. So here, did it say it was normal, yes or no? Did it tell me the distribution is normal, yes or no?
Yes, it says it's symmetric.
It says it's symmetric, and it also said that it is what?
Bell.
It has to say symmetric and Bell, or it has to say normal. Everybody got that? It can't just say symmetric, because there are distributions that are symmetric that are not shaped like bells. For instance, this distribution right here, is symmetric. It's symmetric, but it's not shaped like a bell. I can't use the normal, I can't use the empirical rule for that. It has to be normal or shaped like a bell. So for this, what we're going to do, they tell me that my mean is what? My mu is 64.2, and my standard deviation sigma is 2.9. The average deviation from the mean is 2.9. So what do I do first? What do I label first?
The mean.
The mean. Put the mean at 64.2. And then we're going to add, I'm going to add first. I'm going to add 3 standard deviations to the right. And I'm going to add 3 standard deviations. I'm going to subtract 3 standard deviations to the left. So when I take 64.2 and I add 2.9, I get 67.1 plus 2.9 again. I get 70 plus 2.9 again. I get 72.9. So I've added 3 standard deviations to the right. I'm going to go back and subtract 3 standard deviations to the left. So from 64.2 minus 2.9, 61.3 minus 2.9, 58.4 minus 2.9, 55.5. Does everybody understand what I did? Anybody not sure what I just did? Added standard deviations, subtract standard deviations, right? Once I have the curve set, I can answer these questions. It says, estimate the percent of women whose heights are between 58.4 inches and 64.2 inches. So 58.4 inches is here. 64.2 inches is here. So I want to find the percentage of people inside of here. Right? And I can see where that's at in here. If I go back up here and look at this, I see I'm right here, that's 34%. And right here is 13.5%. So if I want to estimate the percentage of women that are inside of there, I just need to add up 34 plus 13.5, and I get 47.5%. So all I'm doing is I'm corresponding this chart right here, the one I just made, to this one up here, that one I have available to me. What percent of women have a height greater than 58.4 inches? If I want to know greater than 58.4 inches, where am I going to look at? What do I look at? Anybody? Y'all can still hear me, right?
From 58.4 and up.
Okay. Thank you. I just wanted to make sure I know. So 58.4 and up, so I'm going to go this way, right? So when I do that again, I'm looking at the chart. This right here is 34. This right here is 13.5, 2.35, 2.15. I can add all these up. If I add all those up, anybody get an answer right there?
Shouldn't it be 97.5?
Yeah, so this would be 97.5%. You can add them all up that way. You could also go quicker and just subtract off these two from 100%. What I mean by that is this is 2.35 and this is 0.15. This is 2.5. This is 2.5. So you can do 100 minus 2.5, you get 97.5 too. The last question says this, would it be unusual for a man to marry a woman that is 6 feet tall? Explain. When we talk about a normal curve, the good thing about a normal curve, we can give labels. And one of the labels we give is this label of unusual versus usual activity, or something that'll normally happen versus something that doesn't. In a normal curve, usual, the word usual means that you are generally within 2 standard deviations of the mean. So anything that is 2 standard deviations from the mean is considered usual. This is usual. Anything within 2 standard deviations of the mean. This is 2 sigma from mu. Anything outside of 2 standard deviations is going to be considered unusual. Well, if a woman is 6 feet tall, does anybody know how many inches that is?
72.
That's 72 inches. So based off of that information, would it be usual or unusual for a man to marry a woman that's 6 foot tall?
Unusual,
Unusual.
Unusual. Why is it unusual?
because it's like 3% of the people.
Good. It's only about 3% of the people, or because it falls what? Or because we see that it's more than how many standard deviations?
It's more than 2.
Good. It is more than 2 sigma from the mean. So if I actually have something as usual or unusual, I'm actually going to look at the standard deviation. I'm looking to actually look at the mean, and I'm actually going to look at those values and each standard deviations. If you're more than 2 standard deviations away from the mean, it's unusual. All right. If it's less than 2 standard deviations, it's usual. Got that? So this is the empirical rule. This is one application of the standard deviation. This is one way we use standard deviation. And we can only use this rule if the distribution is what again?
If it's Bell and symmetric curve or
Symmetric
normal.
R, if it's normal. If it's one of those three, if it's Bell and symmetric R, if it's normal, we can use it. What happens if the distribution is not Bell and symmetric? Or what happens if we don't know what the distribution is? We have another rule. It's called Chebyshev's theorem, or his Chebyshev's inequality, if you want to call it that too. And it works like this. If the underlying distribution is known to be normal, the empirical rule provides a good estimate for the distribution of the data. However, what happens if the distribution is known to be not normal? We can use this theorem. Here's what the theorem states. The theorem states the proportion of any distribution that lies within k standard deviations of the mean is at least, and it's what we call a conservative rule. It's called a conservative rule. Conservative meaning that is going to give you a lower limit, basically. It can be more, but the lower limit is going to be set. It's 1 minus 1 over k squared. 1 minus 1 over k squared, where k has to be greater than 1. K is the number of standard deviations, right? So an example would be, for instance, if I tell you that k is equal to 2. If I tell you that k is equal to 2, the formula says you do 1 minus 1 over 2 squared. That'll give you the percentage of values that fall within k standard deviations, within 2 standard deviations, is what that's saying, all right? And so 1 minus 1 over 2 squared is 1 minus 1/4, which is 3/4 or 0.75. So 75% of the values fall within 2 standard deviations of the mean. All right, 75% of the values fall within 2 standard deviations of the mean. That's what this is saying. So we can use this if we don't know the underlying distribution, if we don't know that it's normal. If it's normal, we want to use the empirical rule. If it's not normal, though, we have to use this, which is going to be a conservative rule. So what this says, look at the example. The mean score of an insurance commission's license examination is 75, with standard deviation of 5. What percentage of these values of the data set lies between 50 and 100? The question is this: do we know the underlying distribution? Do we know if it's normal or not? Yes or no? Have they told us that it's normal?
No.
No, we don't know that. Because we don't know that, it's required us to use Chebyshev's rule, all right? We want to find out how many values lie between 50 and 100. Well, in order to do that, what we need to do is we need to figure out what's the mean again? What's the mean?
75.
Thank you so much. Mu is equal to 75. The standard deviation, sigma, is equal to 5. I'm looking at values. I'm going to just make this line. We know it's not normal, but we know that the mean is here at 75, right? And I want to know how many values lie between 50 and 100. So how far is 50 from 75? Anybody?
5 standard deviations.
Good. How did you get 5 standard deviations?
The difference is 25 divided by this the 5, which is the standard deviation.
So the
amount.
difference, so good, that's what I want to hear. So the difference here, this is 50, this is 100. They're both how many standard deviations away? They're both 5 standard deviations here, 5 standard deviations there, right? So my K here, K is equal to 5. I'm 5 standard deviations away. That's what this is saying. K is equal to 5. So what percentage of values fall between that then? 1 minus 1 over 5 squared. 1 minus 1 over 5 squared. This is equal to 1 minus 1 over 25, which is 1 minus 96% of the values. 96% of all the scores will fall between 50 and 100. That's what it's saying. That's all we use this for, right? This is a conservative estimate. 5 standard deviations, we know in the normal rule, if you're 5 standard deviations in the empirical rule, all of the data lies within 5 standard deviations. Because within 3 standard deviations, 99.7% of the data. But here, we're using a more conservative rule. So we're saying within 5 standard deviations, it's only 96% of the data. Now, we're using this rule, and it has to be conservative because we don't know the actual shape. If it were normal, we could be more accurate. But because it's not normal, we have to be conservative. This is a lower limit for that value. There could be more. There could be more. We know the least amount, the least is going to be at 96%. All right. So, look at this next one then. Suppose 1,000 applicants show up for a job interview, but there are only 70 positions available. To select the best 70 people amongst 1,000 applicants, the employer gives an aptitude test to judge their abilities. The mean score on the test is 60 with a standard deviation of 6. If an applicant scores an 84, can they assume they're getting a job? Can they assume they're getting a job? So here's what we're going to do. First, I want to know this. What rule do I use? Empirical or Chevyshev's rule? Am I given that the distribution is known to be normal? Yes or no?
No.
No, because it's not known to be normal, we have to use Chevyshev's rule, all right? And what we're going to do with this is we're going to identify the mean. What's my mean here?
60.
Thank you. My mean is 60. And my standard deviation, sigma, is 6, right?
6.
You scored what on your particular test? You scored a 84.
84.
How well did you do with respect to the mean then? How far above the mean did you score?
4 standard deviations.
Good. We scored 4 standard deviations above the mean. Does everybody see why? You scored an 84 minus 60. That's equal to 24, right? Our standard deviation though here is what? What's our standard deviation? 6. So we're going to divide 24 by 6. That equals what then? You scored 4 standard deviations better than the mean. You scored 4 standard deviations better than the mean. That's what this is saying. Now, using Chevyshev's rule then, what percentage of people are going to score more than 4 standard deviations above the mean? Well, again, what do? Or within 4 standard deviations of the mean, we're going to do 1 minus 1 over 4 squared. 1 minus 1 over 16. .9375. Right? Y'all see how I got that?
Yes.
Yes. Everybody understand how I got that?
Yes.
All right. So now here's what we're gonna do with that then. Once we know that, to actually find the probability that a person scores better than you then, what's the probability that a person scores better than you? Anybody tell me that? How to find the probability that a person scores better than you?
Subtract that from 100%.
Subtract that from 100%. Good. So I'm gonna subtract that from 100%. So it's or just one in this case. 1 minus 0.9375. There's what kind of chance a person scores better than you then?
6.25%.
The probability, and that's why right there. The probability that X is greater than your score of 84 is equal to 1 minus the probability of being better than that. That's equal to 0.6025. So do you think there's a pretty good chance you'll be accepted? Yes or no?
Yes.
Yes. There's only a 6% chance that somebody's going to score better than you. Those odds are pretty good that you'll actually be accepted into this job, or accepted into what we're talking about, this interview, based on one of the 70 positions. Right. And again, you can go even further. If it's 6.25 are going to score better than you, that means how many people are going to score better than you? You're looking at 1,000 people, by the way. You're looking at that. So it'll be about 63 people, right? How many people do they take?
70.
70. So you should be one of the top 70. That's what this is saying. 63 people are going to score better than you, so you should be one of the top 70. So you should be okay. All right. And again, that one's a little more involved in depth of what I'm trying to do, but I want you to understand how we use it. On your test, you'll probably see something more like this type of problem, the easier of the two types of problems. Or I'll actually give you the standard deviation, the value for K, and I'll ask you what percentage of values fall within there, all right? But this is an actual application of how you can use this problem in real life. All right. So that is everything to do with the standard deviation. We talked about the coefficient of variation, talked about the empirical rule, and we talked about this thing we call we talked about the Chebyshev's rule, all right? That is everything to do with standard deviation. Are there any questions on that? Any questions to do with standard deviation? All right. Y'all good then? All right. So let's talk about, let's get introduced to bivariate data. Bivariate data now, all right? Bivariate data. So now what we talked about up until this point, what we call univariate data. And we talk about univariate data, the word uni meaning one. So when I think of uni, like a unicorn, for instance, that means one, right? We're talking about, now we're going to move into what we call bivariate data. Bi meaning somebody? Bi meaning what?
Two.
Two. So we're talking about two variable data now. We're talking about two variable data. Bivariate data is two variable data. The two variables are referred to as the first variable, the independent variable here, is what we're going to call our explanatory variable. It's called the explanatory variable because it explains what's going to happen. It's independent. And this other variable is called the dependent variable, or the response variable. So we have two variables, an independent variable called the explanatory variable, and a dependent variable called the response variable. And we're going to display these variables with a new graph. We're going to display these variables with what we call a scatter plot. So we use the scatter plot to display these variables. And the goal is to show some kind of relationship or some kind of trend. We want to show a relationship or some kind of trend between the two. And this is the most important thing. These two variables have to be quantitative variables, which means they have to be numbers that are measuring something. They have to be quantitative variables measuring something. All right. So the goal between this and now is to show that there's some kind of relationship or trend between these variables. And by this relationship that we're going to develop, we're going to talk about this concept that we call independence. Do the two variables depend on each other? Do the two variables depend on each other, or are they independent of each other? So when we talk about this, the first part, when we make a scatter plot, right? And on our scatter plot, here's what we have. When we try to show this relationship, we get three directions of the relationship of the trend, three directions of the relationship or how the patterns are trending. And those directions that we're going to talk about, right? When we talk about the scatter plot, remember, on the x-axis is the explanatory variable, by the way. So that's the explanatory. And on the y-axis is the response variable. That's the response variable, right? And I want to show the trend between those two variables. There are three trends that can be exhibited in a graph like this, right? And here's how it works. We're always interested in what is happening to y as x increases, or as you increase the explanatory, what does the response do, right? And it can do one of three things. As you increase x, y can also increase. And the general trend means that when we talk about trend, we're going to develop this in a second, we look at lines because lines are constant. So the general trend says as this increases, as x increases, so is y. Y is also increasing. That's a general trend. Or you can increase x. So this time as x increases now, y can decrease. So as the x variable is increasing, right, the y variable is decreasing. Or the other thing that can happen is as your x increases, y has no particular trend that you can pick up on. So in the other one, there is no particular trend that is developed. In that particular case, we say that the two variables are independent of each other, right? So if it's positive or negative correlation, the variables depend on each other. But if it's zero correlation, we're going to say that they don't depend on each other. And so when we draw these graphs in, the first thing we always want to do is we want to see if there is some kind of relationship there. And the goal really is to see if there's a bunch of types of relationship, but for our purposes, we want to see if there's what we call a linear relationship. We want to see if we can draw a line through our data. If we can draw a line through our data, we can do this process that we call linear regression or least squares regression. And we'll talk about that in a second. So it says the following data was gathered in one of my high school classes over students' attendance and their scores in the state testing exam. So you have these particular scores, right? And I want to know, does your attendance affect your STAR score? Does your attendance affect your STAR score? That's really what I want to know, right? And so I have the percent of attendance here in one column, and I have algebra STAR scores right here, right? We would expect, and here's how we start bivariate data for the most part. Bivariate data, we hypothesize about something. I would expect the more you attend class, what should happen to your score? Should you have better scores or worse scores?
Better.
Better scores. Everybody understand that? I would expect that to happen. That would be a general trend. The less you attend class, the worse your score should be, right? I want to verify that through graphs and through the actual numbers. So the first thing I'm going to do is I'm going to look at what is the explanatory variable and what are the response. What's my explanatory variable? What variable explains something else? What variable depends on something else?
The attendance is explanatory.
Good. Your attendance is your explanatory. So here's your x. And x is equal, or the explanatory is equal to your attendance. And the response variable, here's your y, The response is your raw score. The next part says, what is the relationship between the two variables? What's the relationship between the two variables? Well, look at the relationship. How do I figure out what the relationship is? Can anybody tell me how to do that? Can I just look at the numbers and tell you what they are? Can you look at the numbers and tell me what they are? Possibly, we can do that.
Did you plot them on a graph?
It's not gonna be easy. We're gonna plot these on a graph. So let's go to the other data set that I have loaded in there, please. The least squares regression data set, and you should see those numbers there. And we're gonna make a new graph. We're gonna make a new graph on my computer. And, share screen. All right, so we have this data set. We have both our data sets loaded in there. Percent attendance and star algebra 1 raw scores, right? We're gonna make the scatter plot now. Excel is very good at picking up on what you want to do by just highlighting things. So we're gonna highlight all of the data here. Highlight this data, and we're gonna go to insert. We're gonna go to insert here, right? So when I go to insert, I want to do recommended charts. If I do a recommended chart, your first chart is going to be your scatter plot, right? Your first chart is going to be your scatter plot, and that's the chart I want to use here. And on this chart, I actually want to make it a little bit bigger. I actually want to add the actual things to the chart itself, the actual variables. So let's try to do that. Format chart area. Text options. Hey, if y'all figure out how to do it before me, let me know. Because I don't really remember how to do it, but I know you can do it. You can add the things to the different axes. Oh, I know axis. Not change chart. Edit all text. I don't want to edit all text.
Is it axis titles?
Yeah, where's that at?
On the
Chart
little
options,
plus sign?
What plus sign?
I just
Help
hovered
me
over
out,
my
what plus
graph and
sign?
there's a plus sign.
And it just popped up. Everybody else can
Yeah.
get that too? Oh, wait. That's what I want to change the axis. I don't know. I don't see it on mine. There's a way to do it. Thank you for finding it, but not being able to tell us how to do it.
Go to get out of what you're on and hover over the graph.
Okay.
Click on it.
Okay.
Yeah, there's a plus sign on mine.
It just popped up with a, oh wait, there it goes. Change. Wait, I know. You're right. Format axis. You have to click on the axis. Click on the axis and go to labels. Click on the axis, go to label. Nope, not that one. I don't know how to do it, you guys. I don't want to lie to y'all and tell y'all I do. I want to put the actual thing on it. There's a way. Oh, text options, maybe. Access to options. I'll figure it out one day and I'll let y'all know. I'll let y'all next class. There's a way to do it. You can change the actual chart title. I want to add the actual things to it. But here, we know that from what we already did in our exploratory stuff, we know that the x-axis is your attendance, the y-axis is your raw score. You click on any one of these plots, any one of these points, it tells you what that point is, right? 6731. So that means a person had a what? What does that 6731 mean? Anybody tell me?
That they had 67% of attendance and they scored a 31 on their raw score.
Good. And we look up here. This person had a 98. This person had a 99% attendance and made a 49. This person had a 99% of attendance made a 49. This person had a 98% attendance, made a 51. So we see when we look at this graph, what's the general direction of the graph? Can you tell me that? General direction, what's it going to be?
Positive.
Positive. What does that mean for positive then? What am I telling you that when it's positive? That means that as your
As your X
what
increases,
happened?
so does your Y.
So what are we saying? What does X stand for here?
Attendance.
So as your attendance increases, as the attendance increases, what happens to your raw score?
It increases.
It increases. That's what I want you to say. As the attendance increases, so does your raw score also increases. That's what this is saying. That gives me the general trend. The general trend is that as attendance increases, raw score also increases. All right. So this is the first thing I want to do. I just want to look at this graph right here, right? So let me come back to what I was doing. Let me take back over screen. So we said as attendance increases, as attendance increases, raw score increases. As attendance increases, raw score increases. Now, here's the most important part we're trying to do. Because we're able to develop a trend, we can see that as attendance increases, the raw score is increasing. I want to try to see if a line will fit this data. So where it says, does there appear to be a linear trend between the two variables? Linear trend means that, here's why I care about lines. Lines go forever in one direction. You got that? They go forever in one direction. So if I were to draw a line through this data, could I draw the line to make it go forever in one direction? Could I make this line go positive and go through most of those points? Yes.
Yes.
Right? So the answer here is yes. A line fits the data. Now, I'm going to verify that numerically through this thing that I call the covariance. This thing I call the covariance, all right? And the covariance itself is just this value that's going to tell me how X and Y are varying together. And generally what that means is that for bigger X's, or as X increases, the Y value should also increase. So for a high attendance, I should have a high test score. For a low attendance, I should have a low test score. So I'm telling you how they vary. And if the trend is linear, that means that for the most part, for all of your high test scores, you should have high, for all your high attendance, you should have high test scores. For all your low test scores, you should have low attendance, right? And so if it's positive, that's what that means. If it's negative, that means that for your low value, you should have high scores. And for your high value, you should have low scores. And if the trend is like a zero trend, then that means everything's bouncing around. We can't really tell. So we can find this thing called the covariance, right? So in order to find the covariance, we use this formula here. We call it we write it like this: covariance of X and Y. And it's equal to this fancy looking formula, which says it's the sum of X minus X bar. Can anybody tell me what X minus X bar is? Anybody tell me what X minus X bar is? I bet you can if you really thought about it.
The mean.
The mean is X bar. What's X minus X bar though?
Standard
Hey,
deviation.
It's not the standard deviation. It's just a what?
The deviation of
Deviation.
whatever number you're looking at.
It's just a deviation. It's just the deviations, right? So X minus X bar times Y minus Y bar. Well, look, why am I doing Y minus Y bar with this? That's because now I have how many variables?
Two.
Two variables. And what I'm actually finding is what we call this part right here. It's telling me to find the deviation of the X and the deviation of the Y and then multiplying. This is a cross product. It's called the cross product. So I'm going to multiply those two values together, and I'm going to divide them by, I'm going to add them all up first and divide them by n minus 1. Why am I adding them all up and dividing them by n minus 1? Why do I add them all up?
To get an average?
To get an average. Thank you. I'm trying to find an average here. That's what I'm actually trying to do. I'm trying to find the average of the cross products, though, of the deviation. So we can do that in Excel as well. There might be a covariance formula. I hope there's a covariance formula.
I think there is.
If not, we will have to do it by hand, but I think there is a covariance formula. I'm almost certain there's one.
There is. There's one for a population and a sample.
Good. Is this a population or a sample, by the way?
Sample?
Sample. So we're going to do this for the sample formula with sample. Let me share my screen. All right, so using this data, I can actually show you how to find it by hand, but we're not going to worry about that. To find the covariance, it's equal to, start typing covariance, and you have population, you have sample, covariance P, covariance S. We said this is a sample. You have to do two arrays, array 1 and array 2. So it means you need two variables. So I'm going to highlight the X's and the Y's. So the X's first, like this. Highlight the X's first, put a comma. Then do the Y's next, put a comma. Close it. There's your covariance, it's 58. A positive covariance means that the direction of the data should be positive. That's all the covariance is telling me, the direction right now. So I want to find the covariance. A positive covariance means the direction is positive. That means, generally speaking, as the X's increases, the Y's are also increasing. So the positive covariance means. A negative covariance, a negative value, means that generally as the X's are increasing, the Y's are decreasing. And it also means I have negative direction. All right. So that's all the covariance is saying. It's just telling me what's happening to the direction of the data based on, it's actually giving a number, it's quantifying it. Positive values mean that they increase. Negative values mean that they're decreasing. A zero value, which will be very hard to get, means that it's 0. But the closer you are to 0, the less you're able to tell the trend. So that's all the covariance is. It's nothing more than that. That's all we're going to do with it, all right? Because the next value we're going to talk about is what we call our correlation. And the correlation is the value that I'm more interested in. All right. So let's talk about this correlation value. And correlation is a measure, it's actually a measure of the, what we call the linear. We say the linear string and direction of two quantitative variables. It's a measure of the linear string and direction of two quantitative variables. Right? So what do I mean by linear string? Linear string means how close to a line is the data. And we're going to quantify that number. Linear string literally means how close to a line. How close to a line is the data? And we already saw the direction means, is it positive, is it negative, or is it 0?
Positive.
Correlate. So we said it was positive. So we want to see, is this value going to be, now we want to see this. So this is what's going to happen. Correlation itself always falls between two numbers. It always falls between -1 and +1 inclusively. We call it the letter R, by the way. So R is equal to, we call our correlation. And R is always in between -1 and +1. A value of 1 means that there is what we call perfect positive correlation. A value of -1 indicates perfect negative correlation. So you have what's called perfect positive or perfect negative correlation. And what that really means is that if it's perfect positive, for every increase in X, Y is going to increase by the same amount every time. If it's negative, for every increase in X, Y is going to decrease by the same amount every time. When I talk like that, does anybody know what I'm talking about when I say increase in X, Y increases? Anybody know what that's called? What am I talking about? I'm talking about a particular thing in math. Let's say in algebra. For every increase in X, Y is going to increase by the same amount. Anybody know what we call that?
It's an M in the formula. I can't remember.
It is
what
a
it's
slope.
called.
Y equals mx plus b. You're right. It's called slope.
Yeah.
I'm talking about slope. I'm talking about slope. So for every increase in X, there's a increase in Y. For every increase in X, there's a decrease in Y. Or for every increase in X, we can't tell what's happening to Y, right? That's what correlation says. And correlation falls between -1 and 1. And here's how it works. We can divide correlation into 3 general terms when we talk about string. That's what's called strong correlation. If it's on the negative side, strong correlation is between -1 and -0.70. Strong positive correlation is between 1 and 0.70. I should write these the other way, by the way. I wrote these backwards. This one should be, no, that's right, that's fine. You just don't see it like that. So +1 and 0.70. That's not right. It should be written like this. That don't look right. It should be written like 0.70 to 1.0. That looks better. I wrote them all backwards. You always write the smaller number first. So moderate correlations between -0.70 on the left to -0.30 on the right. So when you look at that, anything that falls between those two values negative are going to be moderate correlation. Again, this is written wrong. It should be written as 0.30, 0.70. And these are not hard and fast rules, by the way. These are what I use and generally what some books may use, but you won't see it always written like this. But generally speaking is what we say. In between these values are where we're going to fall. Last one, weak correlation. Anything between -0.30 on the left, negative side, to 0. Anything from 0, if it equals 0, it's if it equals 0, it's no correlation. But if it's anything from 0 to 0.30 on the right, it's going to be weak correlation. And generally speaking, you can have an idea of what the correlation looks like by looking at how your values are falling on a line. So in particular, we look at this one, for instance. This is perfect negative correlation. That's perfect negative. Why is it perfect negative? All the values fall on the line like this. R is equal to -1. It's negative because they're decreasing. Here is perfect positive correlation. Here's perfect positive. Again, all the values fall on the line. R is equal to +1. From there, we start to spread out. From there, we start to spread out. So you're going to be in between either -1 and +1, and you're looking at the spread of the values. The more spread it is, the closer to 0 you're going to get. If it's something like this where there is, then you can think of the spread here as drawing a straight line through this. This line, and by the way, has a slope of 0. It's another way you can look at it. You can identify the slope. So the slope is 0. Horizontal lines have a slope of 0, which means there is no trend between them. Here, there is a weak trend between these. Here, there is a moderate trend between these. Here, there is a strong trend between these. All right. But the closer it is to -1 or 1, what do you notice about them? Closer it is to -1 or 1, the more it looks like a what?
A line.
A line. So the closer you are to -1 and 1, the more it looks like a line. The further you get, the closer you get to 0, the more scattered it is, all right? So when we talk about correlation, let's go find the correlation of this data set. It's very simple to find correlation using Excel. There is a formula for correlation, but we will not use it. We will actually use a chart to do this. So in order to find the correlation, let's see. There is the correlation function there. Again, you highlight this, comma, you highlight this, comma, there's your correlation. This value here is R. This is the correlation. This was the covariance. If you look at their values here, R is 0.950488. What does that tell me? Well, it tells me two things. What's the direction of my data? Anybody tell me what the direction is going to be?
Positive.
Is it positive, negative? Is it positive, negative, or 0 is positive? Why is it positive? Because R is a positive value. R will always give you the direction like that, all right? The other thing I want to know is the data strong? Is the line, the linear relationship strong, moderate, or weak based off of R?
Strong.
Strong. So here we're going to say that this correlation is positive and strong based off of R, right? Positive and strong. Now, that's one way to do it. You can use the formula. You can use the actual Excel formula. The other way to do it, and the way I want you to do it, is to use the actual chart. And that's because the chart is also going to give you what we're going to talk about lastly, which is going to be the linear regression equation. All right, linear regression equation. If we use the chart, and you go to highlight your data again, highlight all your data again. That's why it didn't work last time. Highlight all the data, and you're gonna go to insert, and you want to go to your recommended charts, and you have your scatter plot again. All right, bring up the scatter plot again like we just did. The thing that's different about this now is you want to go to quick layouts, and you want to go to this chart right here, the one that has f of x, layout number 9 on mine. I don't know what the number it is on yours, but it should have something that says f of x on it like this. That is telling you it's going to give you a function. And in particular, it is going to give you the linear regression equation. It is going to give you the linear regression equation, all right? That equation, if you click on it, if you click on this new chart, it's going to give you this right here. And this is what I am actually interested in. Make that bigger. Did it make it bigger? It did not. I'm trying to make it bigger so I can see it. Can y'all see it? There. There. This is called the least squares regression equation. All right. And notice this is giving me this value that we call R squared. R squared is what we call the coefficient of determination. So this value right here is what we call R. This value is what we call R. This value right here is what we call R squared. And that is known as the coefficient. I don't know what I'm typing. Coefficient of determination. Right? And that is equal to, in this case, 0.90. I don't want to type equals. 0.9034.
And I'm
That's the
sorry,
value of R
I
squared.
missed it. Where did you get the formula for the y equals?
I did a chart. You have to go to the chart, click on your chart and insert. I inserted it. Let me do it again because I don't see it now. Oh wait, I know where to go. I can't see it because I got these in the way. Go to format, not format. Go to chart design. I'm sorry. If you go to chart design with that chart, you have to go to quick layout over here, right? Do you see it up there?
Yes.
All right, go to quick layout, and on quick layout, you can't see it on your. You can't see it on my screen for some reason. It doesn't come up. It's not showing it. But I'm on layout number 9 right now. I don't know what yours says, but it has an f of x. It has a function. That's what it is. It's writing a function. It's going to give you the least squares regression line. That's what this equation is, the least squares regression line. I haven't gotten there yet, but that's what it's giving me. All right. And if you click that, it'll bring up that actual formula. It should put that formula in there for you. And I'm actually interested in that value R squared because R squared, if I want to find R, how do I find R? Can anybody tell me from R squared? R squared is literally R squared. You understand that? It's literally taking the value of R and squaring it. So how do I find R?
Square root.
Take the square root of this function, right? That number right there. And look what I get. I get a value that's pretty close. They round it off, but that's why I'm getting that. So here is the value of R. I'm showing you this because of 2 reasons. On your test, I'm going to give you an actual chart with that formula on it. That formula gives you everything that chart gives you everything you need. It gives you the direction. It gives you the strength through the correlation through R squared. It also gives you the linear regression equation, which you're going to do things with eventually. All right, but right now, when I look at this, here's the value of R. Here's the value of R. They're pretty much the same thing. They're 0.9505. I'm going to call them that, right? And they both tell me that as your attendance increases, so does your raw score, right? They're both positive and strong, but I'm getting them 2 different ways. I got the correlation from what we call the coefficient determination. All right, you can get it either way, but now I have also the regression equation here. I also have the regression equation. And so now I want to talk about regression in this last part. And then we'll call it a night. I'm probably going to talk more about regression next week too. But I'm going to introduce it right now. Share content, screen. All right, so here. Last thing. Least squares regression line. Least squares regression or linear models. All right, least squares regression line, also known as you may think of it as, when you think of it as, the line of best fit. And it's the line that minimizes. It minimizes the square deviations from the mean. We've been talking about deviations all night tonight. Square deviations for variances. It minimizes the square deviations from the mean. It literally wants to make every value away from the mean as small as possible. And it's a line that does this though. And it's a line because you have bivariate data. You always have the point X bar, Y bar on this line. This line will always have the point X bar, Y bar, which means you will always have the mean of X on the values and the mean of Y. And there'll be a point that sits on the line. It's essentially a mean for bivariate data. That's what you're really looking at. You're looking at a mean for bivariate data. That's what this line is. And we're going to use the line to predict unknown values based on known data. That's our goal. We're going to use that line to predict unknown values based on known data. Somebody said it earlier, the equation for a line, you know the line of best fit. is y is equal to mx plus b, where m is the slope and b is the y-intercept. In the least squares regression line, or LSRL. If you see me write that, that is LSRL. We have an equation that says this right here. Y hat, or actually, yeah, we'll talk about y hat is equal to B0 plus B1 X, where y hat, this is referred to as y hat. It's literally called y hat. That thing above it is called a hat, right? Y hat is a predicted value. It is a predicted y value, some predicted y. And B0 is the y-intercept. And B1 is the slope. And X equals the value at which the prediction is made. This is called the least squares regression equation. And for us, we got a least squares regression equation of y hat was equal to, depending on how you write it, statisticians write the intercept first. We don't have to though. And as a matter of fact, Excel didn't give it to me like that. Excel wrote it like this: 0.5669x minus 7.688. I would actually round a lot of it off right there, to be honest, but this is the actual equation where this part right here is the slope. This part back here is the y-intercept. I can use this equation now to predict a person's raw score based off their percent of attendance. That's what I want to do here. And in general, when we write these equations, we should actually change these variables to what they are. In this case, what I mean by that is this y hat right here is actually the predicted raw score. So we call it raw score hat. That's equal to 0.5669. And your X in this case, your X variable here is your attendance, your percent attendance. So notice I'm calling the variable X attendance. I'm calling the variable Y raw score minus 7.688. And so now I can give you things like, if I said a person had an attendance of 90, right? An attendance of 90%. I said a person has an attendance of 90%. Well, if their X is equal to 90, I want to know what's the Y going to be. If X equals 90, what's the Y going to be? So that's just Y hat is equal to 0.5669 times 90 minus 7.688. You can go to Excel, type that in there if you want to. I can use my calculator real quick. So with an attendance of, with an attendance of 90, right? 0.5669 times 90 is this, minus 7.6888 is this right here. So it looks like they're gonna get a raw score of about 43, right? Since every other raw score is in whole numbers. So y hat was equal to 43 point, what was it? 0.3322. So they get a raw score of about 43. If you go back to the data set real quick, look at your data set. And if you look at values of around 90, let's go back to this data set real quick. If you look at values of around 90, you have 91 and 92 sitting here, right? And then you have 89 sitting here. Those are values around 90, right? Does my answer make sense? Does my answer of 43 make sense? Yes or no?
Yes.
Yeah, it makes sense. It's pretty much aligned with the other values in the data set. Everybody got that? It's pretty much aligned with the other values in the data set. So that's how we're going to use this. I don't want to go too deep into it today, but I have given you enough information to where if we did not meet, if we had another ice storm next week, you could take a test and still be okay. All right. I will go more in depth on other properties of linear regression that I don't think you're gonna see on your test. But I'm gonna talk a bit more about it on Tuesday. Next Tuesday.